Welcome to the Deep Dive. Today, we're looking at a really interesting paper. It's titled Insights into DeepSeek-V3, Scaling Challenges and Reflections on Hardware for AI Architectures.
Yeah, it's a fascinating read. Our mission today really is to unpack what DeepSeek-V3 tells us about, the future of AI hardware.
Yeah.
And how models and hardware kind of have to evolve together.
Exactly. We're getting the story straight from the source. The researchers detailing their architecture, the infrastructure behind this pretty cutting-edge large language model.
And the big question, I think, is how DeepSeek-V3 tackles those inherent hardware limits we have right now. How do you get not just powerful AI, but AI that's actually cost-effective to train and run?
Yeah.
It feels like a glimpse into what's next for AI systems.
Okay, so let's unpack that. DeepSeek-V3, it didn't just appear in a vacuum, right?
No.
The paper starts by setting the scene, this incredibly fast evolution we're seeing with LLMs.
Right. They kick off highlighting that, breakneck pace. They mention models like GPT-4o, Llama 3, Claude 3.5 Sonnet, Grok 2, Qwen 2.5, Gemini 2, and DeepSeek-V3, of course, as examples of just how fast things are moving.
And they really stress the role of scaling bigger models, more data, more compute, basically echoing the scaling laws we hear so much about. That's the engine, right?
Absolutely.
Yeah.
But what's really interesting is this dual pressure. It's not just about making models more capable, but also making them run efficiently, especially, for longer chats, deeper reasoning. They point to models like OpenAI's O103, DeepSeek-R1, Claude 3.7, Gemini 2.5 Pro, Seed 1.5 thinking, Qwen 3, all focusing on that inference efficiency piece.
Yeah, it feels like this massive race. You've got the big tech companies building these colossal training clusters, but then you also have these maybe more agile open source players like DeepSeek, Mistral, really pushing boundaries too.
Totally. And DeepSeek-V3 is positioned as like a milestone in doing this cost effectively. They achieved top-tier performance with only 2,048 NVIDIA H800 GPUs, which sounds like a lot. But in this field...
Right. Compared to some others, it's actually quite constrained.
Exactly. It's pretty remarkable, actually.
So the paper isn't just another rundown of the DeepSeek-V3 architecture, which, as you said, is out there already. What's the real focus here?
Yeah, they're very clear. The main goal is to explore that interplay, that kind of dance between the hardware and the model design. How do hardware limits shape the models? And how do model needs push hardware development? All aimed at building efficient AI at scale.
Okay, so it's about that hardware-aware design, the mutual dependencies, and looking ahead, right? What does this mean for future AI hardware?
Precisely. It's connecting the silicon, the basic hardware, with the complex algorithms running on top and thinking about how they push each other forward.
All right, let's get into some of the nuts and bolts. What are the key architectural innovations in DeepSeek-V3 they talk about, and how did these link up with their hardware choices?
Okay, so they build on what worked in DeepSeek-V2. They mentioned sticking with DeepSeek-Mo and Multi-head Latent Attention, or MLA. Those were already validated.
DeepSeek-Mo, that's their take on mixture of experts. How does that help with the hardware side of things?
Well, the clever part is how it optimizes for sparse computing. So think of it like you have this huge model, but it's made of many specialist experts. For any input, only a few relevant experts actually fire up and do the work.
Ah, okay. So you're not activating the entire massive parameter count every single time.
Exactly, which saves a ton of computation compared to a dense model where everything is always active. It's much more hardware friendly in that sense.
And MLA, multi-head latent attention. That one's about memory, right?
Yeah.
Specifically the KV cache.
You got it. MLA is this really neat way to compress the key value cache. Now, the KV cache is super important for inference, especially multi-turn chats, but man, it can eat up memory.
Right.
MLA compresses those internal states, those keys and values, cutting down memory usage significantly.
They also mention using FP8 mixed precision training. That's about squeezing more performance out of the compute units, yeah. Lower precision, faster calculations.
Pretty much. Using FP8, which represents numbers with fewer bits, for parts of the training, it lowers the computational cost, makes training these huge models more feasible without needing, exponentially more hardware, and crucially, without losing too much accuracy.
And then for speeding up the actual text generation inference, they use this multi-token prediction, or MTP model.
Correct.
Yeah.
MTP is about inference speed using speculative decoding. Basically, the model tries to guess several next words at once using cheaper helper models and then verifies them quickly. Faster output overall.
Okay, and they even optimize the plumbing, so to speak. This multi-plane, two-layer fat tree network for the infrastructure. Sounds very network engineering.
It is pretty deep in the weeds, yeah. But essentially, it's a specific, smart way to wire up all those thousands of GPUs. The aim is to cut down communication delays and overhead between the processors, making the whole training dance more efficient, more cost-effective than, say, standard network setups. Think of it like a super efficient data highway inside their cluster.
So all these pieces, the MOE sparsity, the MLA memory saving, the FP8 efficiency, the MTP speedup, the network design, it all comes back to tackling those big scaling challenges, memory, cost, and speed.
Exactly. Those are the fundamental bottlenecks when you scale LLMs. And DeepSeek-V3's architecture seems like a really deliberate response, designed specifically to work well with the hardware they had available.
Let's dive deeper on memory efficiency. The paper says LLM memory needs are growing faster than HBM capacity. That sounds problematic.
It's a huge challenge. Seriously, the memory footprint of these models is ballooning faster than the high bandwidth memory on the chips is getting bigger. You can add more GPUs, sure, but optimizing memory within the model is just essential now.
And FP8 helps there too, right? They mention it potentially halves memory use compared to BF16.
Yeah, that's a direct saving. Helps fight that AI memory wall.
Okay, now, the KV cache again. Crucial for chatbots, but it becomes this memory bandwidth bottleneck because the computation shifts from big matrix math, GEM, to smaller vector stuff, GEMV.
That's a key point.
Yeah.
Modern AI chips have amazing compute power, FLOPS galore, but often the real limit is feeding them data fast enough.
Right.
These GEMV ops, dominant in KV cache used during inference, they do less computation per byte of memory access. So memory bandwidth, how fast you can move data, becomes the bottleneck. Like a Ferrari engine stuck with a tiny fuel line.
And MLA is the fix here, compressing the KV states. Instead of storing the full key value vectors, it projects them down to a smaller latent vector.
Exactly. And the numbers they quote really show the difference. DeepSeek-V3, 70 kilobytes per token for the KV cache. Compare that to Quinn 2.572B at 327 KB2 or Llama 3.1405B at 516 KB.
Wow, okay, that's a massive difference. MLA seems way more efficient than, say, the group query attention those other models use.
It really highlights MLA's compression power.
They do briefly mention other KV cache reduction ideas too, like shared KV, GQA, MQA, windowed KV, quantized compression, noting they all have trade-offs.
Yeah, GQA, MQA share keys and values between heads. Windowed just looks at recent history. Quantization uses lower precision for the cache itself. They all save memory, but might affect long context handling or overall quality. There's no free lunch, usually.
And looking ahead, they mention alternatives beyond just shrinking the cache, like maybe fundamentally different attention mechanisms. Mamba 2, lightning attention, sparse attention, things that scale better with sequence length.
Yeah, that's cutting-edge research, trying to get around the quadratic complexity of standard attention, which becomes a real killer for super long inputs. Sparse attention focuses selectively. Linear time methods like Mamba try entirely different architectures. Lots of interesting work there.
Okay, let's switch gears to cost effectiveness, specifically with MOE models. The big win, as you said, is lower training cost because you only use a fraction of the parameters per input.
That's the core idea. You get this huge model capacity, but the actual compute needed for each training step or even inference step is much lower because only a few experts are active.
The numbers are pretty stark. DeepSeek-V3, 671 billion total parameters, but only around 37 billion active per token, versus dense models where all, say, 72 billion or 405 billion parameters are always on.
And that directly maps to compute cost. DeepSeek-V3 needs about 250 gigaflops per token. Quinn 72B, a dense model, needs around 394 gigaflops. That huge Llama 405B, a whopping 2448 gigaflops per token.
That's, yeah, a monumental difference in compute demand.
Huge.
And this sparsity also helps for like running these models locally on PCs or on-prem servers because the footprint for a single request is smaller.
Exactly right. Since only a fraction of the model is needed at any given time, you could potentially run it on less beefy hardware. They mentioned DeepSeek V2 getting about 20 tokens per second on PCs with dedicated AI chips.
And they even talk about K-Transformers, their inference engine, running the entire 671 billion parameter DeepSeek V3 on a server with a consumer GPU, still hitting around 20 tokens per second. That makes it much more accessible.
It really does. It opens up possibilities for using these very large models in places where you don't have a massive data center budget.
Okay, now inference speed. How are they making it faster? One thing is this dual micro batch overlap. Overlapping compute and communication?
Yeah, it's a smart scheduling trick. You break the work into small micro batches, then you arrange things so that while the GPUs are computing one batch, the communication network is busy sending data for the next batch, like routing tokens to experts or gathering results, keeps the hardware utilization high, minimizes waiting time.
And for their live systems, they separate the initial processing prefill from the token-by-token generation decode, using different setups for each.
Right, that's a production optimization. Prefill is compute heavy, decode is memory bandwidth heavy. So they tune how they distribute the work differently for each phase to maximize throughput for their online service.
But MoE inference still has limits. The paper says the interconnect bandwidth and network speed between GPUs is a major bottleneck because of that all-to-all communication for expert parallelism.
That's a critical point. Every token needs routing to its experts, then results gathered back. That means a lot of data flying across the network connecting the GPUs. The speed of that network directly limits how fast you can generate the next token.
They give some theoretical numbers. With standard 400 GBPs InfiniBand, the limit might be around 67 tokens per second per step. But with something like the future GB200 NVL72 interconnect, theoretically 1,200 tokens per second. That's a massive jump.
It really shows what much faster interconnects could unlock for MoE inference speed. Now, that 1,200 is purely theoretical, assuming nothing else becomes the bottleneck, but still, it highlights the potential of future hardware.
And software helps too, this multi-token prediction framework.
MTP is really cool. Instead of predicting just one next word, it tries to predict several possibilities in parallel, using efficient little helper modules. Then it verifies them quickly. It reduces the overall time to get a sequence out, even if the raw throughput might dip slightly.
And they saw an 80-90% success rate predicting the second next token, leading to almost a 2x speed up in effective tokens per second.
Yeah, that's a significant real-world gain. Shows that smart algorithms can really boost speed without needing new hardware.
And they mention why speed is so crucial for reasoning models like OpenAI's O1 or for things like reinforcement learning workflows.
Definitely. For complex reasoning, if each step is slow, the total time just becomes unusable. And in RL, you often need to generate tons of experience data super fast to train the agent. Inference speed is key there.
Okay, let's talk low precision. DeepSeek-V3 uses FP8 mixed precision training, a first for open source large MoE models, they say.
Yeah, that was a big deal. Took close work between their infrastructure and algorithm teams, using FP8 strategically fine-grained, tile-wise for activations, block-wise for weights, lets them tap into those efficiency gains.
But they hit some snags with current hardware using FP8. Something about accumulation precision in tensor cores and overhead from dequantization with that fine-grained approach.
Right. The paper notes that how current tensor cores sum up FP8 results can sometimes cause numerical issues in really big models, and that fine-grained quantization, while good for accuracy, means extra steps moving data between tensor cores and CUDA cores for scaling factors, which adds overhead.
So what do they suggest for future hardware? Better FP8 support.
Basically, yeah. Increase the precision for accumulation, maybe make it configurable, and build native support for handling those fine-grained scaling factors inside the tensor cores, like NVIDIA's Blackwell architecture apparently does with microscaling. Avoid that data movement tax.
Interesting. They also experimented with something called logarithmic floating point formats, log-FMT, for communication compression.
Yeah, log-FMT is a different way to represent numbers.
Yeah.
Using a logarithmic scale, it can potentially represent a wider range with the same bits, especially for activations. The idea was maybe it compresses better for communication. Their tests showed log-FMT 8-bit actually beat standard FP8 formats on accuracy sometimes.
But they didn't end up using it in DeepSeek-V3. Why not?
The main hurdle was the overhead. Converting back and forth between log-FMT and the standard formats the tensor cores use. It was too slow on current GPUs, not enough specialized hardware for log-X calculations, and it put too much pressure on registers. So, promising numerically, but not practical architecturally yet.
So the suggestion is future hardware could maybe have dedicated decompression units for FP8 or custom formats like log-FMT.
Exactly. Hardware acceleration for that could make these formats much more viable for cutting down communication bandwidth, which is a huge deal for training massive MoE models.
All right, shifting to interconnection-driven design. They trained on H800s, lower NVLink bandwidth within a server than H100s, but lots of fast InfiniBand between servers.
Right, and that specific hardware mix really shaped their strategy. The slightly slower within-server communication meant some parallelization approaches weren't ideal.
Like avoiding tensor parallelism during training mostly, because of that NVLink limitation, though maybe using it selectively in inference?
That's the idea. Tensor parallelism splits the big math tensors across GPUs in one server. It needs super fast interconnects like high-end NVLink. The H800's NVLink, while fast, maybe wasn't quite fast enough for their scale with TP during training, so they focused elsewhere.
But they did enhance pipeline parallelism with something called dual pipe to overlap computation and communication better.
Yeah, dual type is a smart way to keep GPUs busy. It runs computations for different model stages concurrently with the data transfers needed between them, both for attention and MoE layers, reduces idle time, improves efficiency, and helps balance memory usage.
And with all those InfiniBand cards per server, they went big on expert parallelism across servers. They even open sourced Deep8 for that all-to-all communication.
Right. That powerful scale-out network. Let them spread the MoE experts across a big cluster. Crucial for hitting that 671 billion parameter count.
Now, this bandwidth difference, NVLink inside versus InfiniBand outside, like 4-to-1 they say, led to this node-limited routing for picking experts. Sounds complicated.
It's a bit involved, yeah. But the core idea is, don't just send tokens anywhere across the whole cluster if you don't have to. Group the experts smartly. Try to route tokens to experts that live on a smaller set of nearby servers. That way, you can use the faster NVLink within those servers to help forward the tokens, minimizing reliance on the slower inter-server links.
Okay, so it's balancing the traffic, using the faster local links when possible.
Precisely. It's designing the algorithm with the specific network speeds in mind.
They also point out limits in how scale-up within server and scale out across servers work together now. Like the main GPU cores get bogged down managing communication tasks.
That's a really key insight. Right now, when data moves between servers, or even GPUs in the same server, for things like combining expert outputs, the main compute cores on the GPU often handle that traffic management.
Meaning they aren't doing the actual AI math.
Exactly. It eats into the compute resources available for the model itself, hurting overall efficiency.
So their vision for the future is a more unified communication framework, maybe dedicated coprocessors just for network stuff?
That's the direction they suggest. Offload communication tasks from the main GPU cores onto specialized hardware. Could be coprocessors, could be integrated into the GPU's I/O system. Let the main cores focus on computation. They mention things like UEC and UA-Link as potential future interconnect standards that could enable this.
And they also flag issues like bandwidth contention, like KV cache transfers over slower PCIe fighting with expert parallelism traffic over InfiniBand.
Yeah, that's a classic distributed systems problem. Different data flows competing for the same pipes. Moving that big KV cache between CPU system memory and GPU HBM over PCIe can definitely interfere with time-sensitive network traffic on InfiniBand.
Solutions proposed: dynamic traffic prioritization on NVLink PCIe, integrating NICs directly onto the GPU I/O die, using NVLink for CPU-GPU connections too.
All aimed at smoother, faster communication. Prioritize critical traffic, bypass bottlenecks like PCIe by putting the network interface closer to the GPU, and use the fastest links like NVLink for everything important, even connected to the CPU.
Okay, let's look at their large-scale network design. This multi-plane fat tree, MPFT. What's the gist?
MPFT is how they wired up their cluster. Each server has 8 GPUs, 8 InfiniBand NICs. They configured it so each GPU NIC pair works on its own plane or independent network path, plus a separate Ethernet NIC for storage. It gives massive bandwidth and low latency, and it's relatively cost-effective for big setups.
The ideal would be multi-port NICs using all planes at once, acting like one super NIC, but current hardware isn't quite there yet.
Right. The dream is the NIC intelligently spraying data across all paths and reassembling it, handling out-of-order packets. That needs serious hardware support. Newer stuff like ConnectX-8 supports multiple planes, but full hardware bonding like that would be a big boost.
But the MPFT they build has advantages. It leverages existing optimizations, like in CCL's PXN. It's cost-effective, isolates traffic somewhat.
Exactly, and their tests showed it performed really well. All-to-all communication was similar to a standard multi-rail fat tree, thanks to NCCL's smarts. And EP-specific communication hit really high bandwidth on their MPFT setup.
And they even compared actual DeepSeek-V3 training on MPFT versus MRFT and got nearly identical performance. That really validates their choice.
Yeah, that real-world test is key. Shows the MPFT design works great in practice for training these huge models.
The paper also talks about latency being super critical for inference, especially for MoE, which needs both bandwidth and low latency. And they compare InfiniBand versus RoCE, Ethernet.
The usual trade-off, InfiniBand generally has lower latency, which is great for sensitive workloads, but it can be pricier and maybe scale slightly less easily than RoCE, which uses standard Ethernet gear.
So they suggest ways to make RoCE better for AI. Specialized low latency switches, better routing, better congestion control, and things like InfiniBand GPU Direct Async, IBGDA, allowing the GPU to manage network control directly.
Yeah, making RoCE lower latency could make it a strong, cost-effective alternative. Better switches, smarter routing, robust congestion handling tailored for AI traffic, and definitely broader support for tech like IBGDA, which cuts CPU overhead and latency by letting the GPU talk more directly to the network.
Okay, wrapping up, the paper zooms out again, summarizes the hardware limits, future directions. They mention robustness challenges, interconnect failures, silent data corruption becoming bigger risks at scale.
Definitely. As systems get enormous, the chance of something failing or data getting subtly corrupted goes up. They stress needing better error detection correction beyond just ECC memory, plus good diagnostic tools for users to check system health.
Also, CPU bottlenecks again. PCIe limits, needing high memory bandwidth even on the CPU side, needing strong single-core CPU performance, suggesting direct CPU-GPU links like NVLink or tighter integration.
Right. As GPUs get faster, the CPU and its connection can become the weak link. Need tighter coupling, higher bandwidth links between them, so the CPU isn't holding things back.
And their vision for intelligent AI networks. Co-packaged optics, lossless fabrics, adaptive routing, fault tolerance, dynamic resource management. The network becomes an active player.
Absolutely. Moving beyond passive pipes to an intelligent, adaptable network fabric designed for AI's unique demands. Huge bandwidth via optics, super low latency, resilience, dynamic adaptation.
They even get into memory semantic communication, ordering guarantees in hardware, proposing concepts like region acquire release. Sounds pretty deep.
Yeah, that's about making data sharing across distributed systems more efficient and reliable at the hardware level, reducing software overhead for synchronization.
And finally, in-network computation for EP. Maybe hardware protocols for replicating aggregating data in the network, native log FMT support, plus memory-centric ideas like DRAM stacked accelerators or system on wafer.
Really forward-looking stuff. Offloading casts to the network itself, using novel formats efficiently, and tackling the memory wall head-on with 3D stacking or even whole systems on a single wafer. Big ambitions to keep AI scaling.
Wow, okay. That was indeed a deep dive. So pulling it all together, what are the main takeaways from DeepSeek-V3 and its hardware reflections?
I think the biggest thing is just how critical that hardware-software co-design is. DeepSeek-V3 shows you can get amazing results efficiently, even on somewhat constrained hardware, if you design smartly for that hardware. We saw tons of innovations targeting specific bottlenecks, memory compression, network design, low precision. It's a really valuable case study.
Yeah. And what were the aha moments for you during this?
For me, seeing those concrete efficiency numbers, the low KV cache size, the reduced GFLOPS for MoE, really drove home the impact of their design choices. Also, that huge potential jump in inference speed from better interconnects was eye-opening. And just a consistent theme. Future hardware needs to be memory-centric and network intelligent. It's not just about raw compute anymore.
Right, the whole system has to evolve together. So a final thought for our listeners to chew on.
Well, think about how these hardware advances, driven by models like DeepSeek-V3, aren't just about making AI more powerful. They're also key to making it more accessible, more deployable. How might that change things? Lowering the barrier to entry for state-of-the-art AI could reshape industries, research, maybe even daily life. This interplay between hardware and software is really shaping that future, and this paper gave us a great look under the hood. Definitely worth pondering the implications.